That's Jack in the background. I'm playing I'm playing a version of the PowerPoint that I'm going to show you that Jack did and recorded last year. So you're going to hear my tired old stories now as I go through the PowerPoint. If you want to hear Jack's version of it, his tired old stories, then you can go back there and do that as well. Okay? So it's slide by slide as you go through the slides. I got to change versions on here. Otherwise, we're going to be hearing them in the background all the time. Or I could just turn the sound down in the background. Maybe I'll just do that so I don't have to restart this whole thing. Well, you know, I can do it this way. Good. Stick with this then. Okay, so I'll go through this, and then we'll talk. We'll play around with the equipment. We'll set it up. I'll show you. We'll do some calculations. I got some sheets to hand out to you. I don't think Jack did that the last time, but and then next week we'll set this up, and you'll actually do some measurements. We have an environmental chamber. It's a fancy name for a plywood box that we have in the back that we set up. We blow some dust into it. You set up your sample train, and we sample it, and then we do some weights before and after. But so we'll actually get a chance to do it. So everybody here will at that point have a good idea of how to do this stuff if they're called to do it on the job. And in fact, part of what we're going to talk about is where you figure out where you get the information about how you should sample, what kind of sample you should use, how long you should run it, what kind of pump you should use, and so on. And it's not a mystery. It's actually pretty easy to find out. Okay, be familiar with this, sampling of gases, vapors, particulates. Why sample? Because we got to know if we're in compliance, right? OSHA compliance might be an issue, might be odor complaints, might be assess whether or not your controls are good if you put ventilation. Anybody here take industrial ventilation? Right? That's kind of a course that's kind of disappeared a little bit here. They do some, I guess, in industrial hygiene, I guess, or in the industrial hygiene lab.
I'm going to take it later on.
Yeah, I taught the industrial ventilation course once, and I love that course. I would love to do that again. I think that's probably one of the most important courses that you could take here in industrial hygiene, because everything you do is about containing contaminants. It's the most effective way of protecting workers is local ventilation. Keep the material from getting into the worker's breathing zone rather than to try and deal with it once it's in his breathing zone. Okay, that's why we have hoods here that are not working. Doesn't sound like. Okay, but anyway, so whatever's in there is getting out into the room now. Are they working? It looks like they're off. At any rate. Yeah. No, you should see a digital readout if they're running. Okay. I don't think there's anything really interesting. It is running? Yeah, I don't think so. Don't worry about it. There's nothing in there. I'm sure there's nothing in there that's dangerous. So at any rate, okay. And also, for academics, because we want to know about these kinds of exposure. We want to measure them and evaluate them. Okay, as we were talking about, there's one of the things we might be interested in doing is screening whether or not there's an issue involved. You guys ever use Draeger tubes and stuff like that? There are direct reading instruments. Some of them could cost $20,000 or $30,000, very elaborate, very technically sophisticated equipment that you can use to do short-term readings for different kinds of contaminants. Could be particulates, could be volatile organic compounds. There are also relatively inexpensive ways to do this. There's an outfit called Draeger and American Sensodyne. They make these little colorimetric tubes that use with a hand pump. And each time you pump it, you push 1/10 of a liter of air through that tube. And depending on what contaminant it's designed to detect, you get a color change. And the length of the color change gives you the concentration of that material in the air. Is that good enough for your OSHA PELs? No. But it's good enough to say that, gee, let me just test this area, because it's kind of like worst case this time of the day when he's doing this. Let me just take the air in this area and get an idea of what the levels are, and maybe you may find that the levels are less than 10% of the PEL. And you may say, well, it's not really worth getting into elaborate testing because I'm not anywhere near the PEL at the worst case scenario, right? On the other hand, you might find that the amount that you measure is 50% of the PEL. Should you do testing then? Probably should, right? You should do 8-hour monitoring. Why is that? What do you think the accuracy of these tubes is? Right? It's plus or minus 35% is the published accuracy of the tube, right? So they're not very accurate, but they're pretty specific, and they're a cheap way to, like, at least get some sort of readings. Okay, so you want to do some screening. If you need to, you can do full shift measurements for the PEL, and you can also, in certain situations where you have a lot of workers exposed, you're not going to check every worker. You want to probably have some sort of strategy for sampling workers randomly or sampling them according to different kinds of work that they do. You want to make sure you cover the worst case scenario, the worst kind of activity, the time of the day that they might be most exposed, right? So you got two issues here. One is you're concerned about temporal exposures. In other words, what time is the exposure taking place? And you're also concerned about geographical exposures. Is it in this area of the plant as well? They're doing this activity. So those are a issue. Okay, what is the dose? What is the exposure that the worker has? Well, it's equal to the concentration in air times the duration that he's exposed to, right? If the concentration is high, but it's a short exposure, it's unlikely you're going to exceed the PEL, right? Because that's an 8-hour time-weighted exposure. That the length of time is so short, it's unlikely that on the average you'll exceed that. Does that mean that you necessarily didn't exceed the PEL? PELs are not just 8-hour time-weighted exposures in some cases. Some of them also include short-term exposure limits. Might be for 15. In other words, for carbon monoxide, I'm going to guess that the PEL now is 35 ppm. I'm not sure. 35 ppm. But the short-term exposure limit might be 50 or 100 for 15 minutes. Right? We could look that up. I don't know. For formaldehyde, there might be one. For glutaraldehyde, there might be a different one. But we could actually look that stuff up. Okay. PEL for toluene is 200 ppm or 750 milligrams per cubic meter. Those are equivalent concentrations in different units. It's important that we understand how to convert between the units, because some of the PELs might be expressed as ppm, some as milligrams per cubic meter. The ones that are expressed as ppm, you might send out a sample, and the lab gives you back information in milligrams. So you got to be able to work with that. But industrial hygienists love doing conversions. That's the best part of the job. They're really great fun. And they're especially fun nowadays because you have things online where you can just go to and fill in the numbers and they'll do the conversions for you. But since we're learning this, we're going to actually wind up doing some conversions ourselves in a little bit. Air sampling units, milligrams per cubic meter. ppm equals parts per million. 1 cubic meter of air is the same thing as 1,000 liters of air. If you think about that, you know that's true. What's a cubic meter? A cubic meter is 1 meter by 1 meter by 1 meter, right? So that's a cubic meter. A liter is 100 cc's, 100 cubic centimeters. So if you just think of 100 cc's as a tenth of a liter, 100 cc's, 1,000 cc's is 1 liter, right? So let's think about that. If you think about that side, that's a meter, then 100 centimeters is 1/10 of that size. So it's 10 by 10 by 10 by 10, which is 1,000. Each 100 cc's by 100 cc's by 100 cc's, you multiply it out, it comes out to 1,000 liters. So each one of those 10 times 10 times 10 is 1,000 liters. Trust me, I was hoping to make you visualize it. Trust me, a cubic meter is the same thing as 1,000 liters. Okay, and we might be dealing in cubic feet, in which case we have to convert into square inches if we want, and then into cubic meters and so on. Most of the stuff we're going to be working with, we're dealing with cubic meters. Let's talk about this idea. The milligrams per cubic meter is pretty clear, right? Milligram is weight or mass, really mass, but we use it as weight because pretty much universally. It's the amount of weight of a material in air, when we're in a cubic foot of air. When we're talking about dust or particles, it's pretty clear. We're gonna take a filter, suck a cubic meter of air through it, and we're gonna see how many milligrams of dust was in the air, and that's our cubic meter, the milligrams per cubic meter. That's pretty clear. Milligrams of a vapor in air is a little bit different because there's a problem. When we're dealing with dust in air, we're dealing with just directly milligrams per cubic meter. When we're dealing with water solutions, like for instance, if I told you there was 100 parts per million of lead in your drinking water, right? What that means is that there's 100 pounds of lead for every million pounds of water, or 100 ounces of lead for every million pounds of water. Actually, you never see those levels. It would be a part per billion. It would be more a bad level in your drinking water, and something exceeding the action level would be 15 pounds in a billion pounds, 15 parts per billion in a billion pounds of water. So it's a weight to weight ratio. But when we're talking about a gas in air, like for instance, if we have benzene evaporating into the air, it's gaseous benzene in air. Parts per million in gases is volume to volume. The volume that a certain amount of a volatile organic chemical takes up is related to its molecular weight, right? So 10 grams of benzene takes up is a different volume of benzene, that is a different volume of that gas than 10 grams of carbon monoxide or 10 grams of ethanol, right? So we got a problem. Well, when we get to it and do some conversions, when we talk about ppm and we're talking about a gas, we have to convert from weight, if that's what we know about it, which is usually what we know about it, into volume. So we'll get to that and we'll play around with it. Now, air sampling, we're actually, there's a couple of ways for us to deal with air sampling. One way is a really nice, simple way is to just capture the air, right, in a vessel that's been pre-cleaned, evacuated and pre-cleaned, and just send the air to the lab and have them tell us what's in it. Most of the time, that's not what we're doing. Most of the time, what we're doing is that we're capturing what's in the air and sending only the contaminant to the lab to find out how much of that contaminant was present. So if we're talking about dust, we're taking a regular media filter, taking a filter, weighing it, sucking air through it, and then reweighing the filter to see how much of it was present. We're sending it to a lab and asking them how much is present. If we're taking a vapor in the air, what we're doing is we're taking, instead of a filter, we're taking a material that will absorb it, like activated charcoal. And we're sucking air through the activated charcoal. We send the activated charcoal to the lab, and they tell us how much of that chemical was in the air. So that's in milligrams. They're going to report that to us. So now we got to deal with our conversions. But in one case, we're capturing the contaminant. In the other case, we're just sending the entire volume of air to it. We'll play around with that. Okay, sampling media could be, now Sumacan, there's no picture here. Oh, it's unfortunate. Okay, anybody know what a Suma canister is? They're really not, nowadays they really shouldn't call them Suma canisters. It's like calling a refrigerator a frigid air. In the old days when I was a kid, you called a refrigerator a frigid air because that's the main manufacturer back in those days. Now everybody makes them now, right? But just like you call a copier. Do they still call copiers Xerox machines? Sometimes, right? Right. Are they always Xerox machines? No, they're usually not Xerox machines now. Now they're Canon and it's, right? Whoever they happens to make them. But they call them Xerox machines because they were the first ones to make them. And their name kind of got attached to them. Right? Same kind of thing. Suma canister is a stainless steel canister, may have a liner in it, like a Teflon liner or something like that. And the lab flushes it out with pure nitrogen and then evacuates it, puts it under a vacuum for a long time, takes all the air out of it. So you can go into a space and just open a little valve on it and do a grab sample of air. It fills it. Could be anywhere from 1 liter to 5 liters. They have like big kind of bulbous tanks that they use sometimes. There might be a picture in here a little bit later on. And you can just capture the air, send it to the lab. The lab will then analyze that gas to see how much of, say, benzene or gasoline or whatever you're looking for happens to be in there. In fact, there is a particular analysis that they do that's pretty extensive for indoor air. We'll talk about it in a second. The other way we can do it is the way I described. Use a collection tube to an absorbent material. Suck air through it. It absorbs the contaminant. And we know if we suck a cubic meter of air through that tube that we've captured all these material that was in the air in that tube. And if the lab can tell us how much is in that tube, then we know how much was in the air. There can be different kinds of sorbent materials, depending on what the material we're looking for. Activated charcoal is the most common because it absorbs a lot of kinds of VOCs. Silica gel, Tenax, there's a whole bunch of different materials depending on the chemical you're looking for. Impingers, anybody here ever see an impinger? Know what an impinger is? That's there. They've really decided. I think we got one over there somewhere. I'm sure I saved at least one. What they are, let's say that there's a gas in the air that is acidic. It's an acid gas, right? You can make a solution up of sodium hydroxide. Let's say you very carefully produce a solution of exactly 1 molar sodium hydroxide. And what you can do is you can take a pump and suck air through a little device that will force the air to bubble through that solution. So if there's any acid in there, it's going to neutralize some of that sodium hydroxide, right? And then when you're done sucking air through it, you can analyze to see how much sodium hydroxide is left, so you know how much acid gases were in the air. That's called an impinger. Okay, well, hopefully I'll get a picture up here soon, and we'll get a look at it. But if not, I may be able to dig one out. We'll take a break halfway through, and or about 2/3 of the way through, and set a couple of things up so you can do something interesting rather than listen to me drone on. Filter cassettes. Those are a situation where we're talking about dust in the air. It could be dust that we want to measure the weight of, or in the case of asbestos, are we interested in the weight of asbestos that's in the air? No, it's a different process. We want to know how many fibers are in the air. We still use a filter, different analytical process. We're going to actually do that. Anybody ever sit down and see somebody counting asbestos fibers on a filter? Well, good for you guys because you're going to do it yourself. You're going to see what a tedious, nasty job that is. Okay, and how it's done. Okay, and passive diffusion sampler. You've seen these badges. Sometimes you might use them in hospital where you hang a badge on a guy's collar, and it's a diffusion device. It absorbs the material that might be in the air. At the end of the day, you write on it how long he was exposed to. You send it off to a lab, and they send you back a report that this was in an environment that had an average of such a level of formaldehyde. Okay, those are passive devices. Okay, organic sampling methods, we'll deal with that. Also, we have direct reading instruments as well. We'll get into that later on in the semester and actually play with a few of those things. You guys have any at the hospital, like PIDs, photoionization detectors, or any of that kind of stuff? No? You ever rent them? No? Okay, there's all sorts of direct reading devices. There are devices that you can use, take into a space, has a digital readout, that you can read how much of a contaminant is in the air right on the device. Parts per million.
We do have the Quattro. That's not really like advanced.
Is it like that's an indoor air quality monitor, CO2 or something like that?
Yeah, it reads like
Oh, it's like a monitor for in confined spaces or something like that. Probably oxygen. And but it's a direct reading instrument. May not specifically be contaminant. The only contaminant that probably checks for is either hydrogen sulfide or carbon monoxide, low levels of oxygen, explosive gases, which is organic vapors, and probably that's probably about it. Okay, so at any rate, so there are these devices that will measure the amount of VOCs that are in the air, like photoionization detector. We'll play around with that. Anybody think of another one? Another direct reading instrument for a material that you just get the reading right there? Yeah.
We work at an indoor air quality place, so we have the ones with VOCs. We also have a lot of moisture meters.
Oh, there you go. Okay, good.
So you can do pin or you
Yeah.
can do like just
Oh, yeah, exactly. Just shove them into the wall, or they're right. Yeah. Bingo. You just mentioned lead. What about lead? Right? How about paint? Direct reading instruments. There's a thing called an XRX, X-ray fluorescence device where you can hold it against the wall and you can actually get a reading of how much lead is present in that wall. You don't have to send the sample to a lab. You can get a direct reading right away. We have one of those here, and we're going to be playing with that when we get to the. We're going to try and expose you to every toxin that's available, in the city. So, you'll be exposed to lead, asbestos, everything else by the time you're done here. Mold. Yeah, there are particulates, direct reading instruments. They're optical devices usually, where they have an area where you can expose, you pull the dust through it, and some of them actually what they do is they have an atmosphere that's saturated with a solvent, and the particles cause it to condense, so it affects how much light goes through it, and you can actually use it as a particle counter. Some of them can even distinguish between different sizes of particles, which is kind of neat, which is important also. Okay, solid absorbent material. We'll get to this. Okay, one of the things we're going to work with here is that we're going to be describing shortly different kinds of pumps, right? We're going to have very low volume pumps, medium volume pumps, high volume pumps. Anybody have any idea why we might have different volume pumps? I can think of two reasons that we might have different volume pumps, two big reasons. Right? Yeah.
I mean, just for the size of the space that you want to measure?
Well, it's not really the size of the space so much as the accuracy that you want to measure it to. In other words, if you want, all of these measurement techniques have certain limitations. So if your PEL says you have to know down to 10 parts per million, how much it is, well, this material is present in the air at 10 parts per million, you might be able to do that by pulling only 10 liters of air through a sorbent material, because that's how accurately the lab can give you the results. But if you need to know down to 10 parts per billion, right, and it's or if you need to know lower levels, or if it's a contaminant that you need a larger, that you only expect to be in the air at 10 parts per billion, very low levels, you might need to pull a lot of air through that sample to get it to the point where that sorbent material has enough of the material for the lab to detect it, right? So the volume. So you don't need a big pump. You don't really need a big pump for that purpose. But if you don't have it, you're going to be sampling for a lot longer time. So in some cases, you got to sample, like for asbestos, the level at which we want to be able to count fibers, use a very high volume pump. And why do they do that? Because if you use a low volume pump, you'd have to leave it there for weeks to get the levels, to detect the levels of fibers that you're limiting it to, right? So you really need a lot of volume of air. On the other hand, in a lot of cases, you're using these like very thin filters for capturing particulate, and if you go pull air through the filter too quickly, you can damage the filter and get stuff going through it and stuff like that. So the volume has to do with the accuracy and the amount of time that you have to run the sampler, right? And also mechanically the media that you're using to capture it. If you're using activated charcoal, you can't go too fast. What'll happen if you go too fast through the charcoal?
I was thinking stuck or something.
What's that?
Stuck. But I know that's not it.
The activated charcoal takes time to absorb the material,
Okay.
right? So you'll get breakthrough. In other words, it won't capture all. If you suck air through activated charcoal too fast, you need a certain amount of contact time to take it out. So if you suck it through too fast, you wind up with some of the contaminant getting past the activated charcoal. So you think that there's less in the air than there really was, right? If we look at these little activated charcoal tubes, you're going to see they have two sections, and we're going to find out why they have two sections in just a little while, right? So the flow rates have a lot to do with how the test works. There you go, right here. Now, what do we got here? We got, these are all sorbent tube materials, right? Different types of, you can see some of them are white, black, different kinds of sorbent materials depending on the specific contaminant that you're looking for. So we get a closer look at that. Activated charcoal, collection of non-polar organic vapors, boiling points greater than 100 degrees centigrade. That's a lot of liquids. Okay, liquid materials at room temperature. High moisture levels can reduce efficiency. Why high moisture? Why does high moisture reduce the efficiency? Because the activated charcoal absorbs the moisture from the air, right? Just like it absorbs a lot of other stuff. Silica gel is generally used to collect more polar substances, not effectively absorbed by activated charcoal. So just keep in mind that you might need to use a different kind of sorbent tube depending on the material you're trying to measure. How do you know which one to use? Do you know which one to use because you know whether the organic molecule is polar or nonpolar? You might if you're really smart, you know? But you don't have to be that smart. We're industrial hygienists. We're not really that smart. If we're that smart, we'd be doctors, right? But you don't have to be that smart because you don't have to invent the wheel. All of these procedures, especially the ones that have PELs associated with them, have specific procedures that have been written out by NIOSH on how you have to sample, what equipment you have to have, what kind of sorbent tube you got to use, what kind of velocity the pump should be using, what kind of filter, what size of the filter, what material of filter. All this is spelled out for us. So when you need to, if somebody says to you, "Oh my God, we have a problem over here in this area of the shop. They're using MEK, methyl ethyl ketone. It's a solvent, right? A neurotoxin. They use it for metal cleaning. They mix it with paint as a paint thinner and stuff like that. Paint removers have it sometimes, right? We have a problem in the shop. We're concerned. We want to measure these. We want to do monitoring for our workers for MEK. What do you do?" If the guy says, "Oh, you're an industrial hygienist. Take care of this," right? What do? Well, you go to the NIOSH website, actually OSHA website or CDC website. I think you get to it now, right? You go to NIOSH and you look up the procedure for MEK, and there'll be a specific procedure tell you exactly how to do it. What's the other way you can figure out how to do it? What are you going to do with that sorbent tube when you're done? Going to send it to the lab, right? What's the lab going to do when they get it? They're going to analyze it, and then they're going to send you a report. What else are they going to send you with that report? A bill. They're going to send you a bill. They don't do this stuff for free. They're going to send you a bill. So it's in their interest to make sure that you know how to do this, and they make it easy for you. Most labs will tell you what you need to do. Oh, I got a sample for MEK in a workplace. What do I need? Oh, you need sorbent tubes. We'll put that together. Do you need to rent a pump? Do you need this? Do you need that? Most of these labs will rent you equipment. They'll rent you the sampling train. They'll rent you everything you need. If you have the equipment, great. They'll just send you the sampling devices and tubes and so on and so forth. They'll tell you what procedure. They'll tell you specifically for their lab if there's something special you want to do with it, handle it. They'll send you a chain of custody, tell you what to fill out on it. They will hold your hand through the whole process. EMSL here in the city. If you want to test the cooling tower for Legionnaire's disease, right? What would you do if you had to test the cooling tower for Legionnaire's disease right now? Would you know what to do? You call up Ellen Podell, my friend at EMSL. She happens to be our sales rep. There's a million of them right over there. Call her up, Ellen. I got to somebody told me to test this cooling tower at our hospital for Legionella. What do I do? So, here, I'll send you a procedure. This is your sampling procedure. This is how you preserve the sample. The sample that you got to use our bottle. Our bottle's got a little tablet with sodium bisulfite, which neutralizes the chlorine, which is part of the procedure. You got to fill the bottle. Don't let the little tablet fall out. Close it up. Get it from here. Don't get it from right where the water's coming into the cooling tower. Get it from here. This is how you do it. Hold it underneath. This is what you do. Send it to us. It's got to be kept at this temperature until it gets all that. Got to get to our lab within 12 hours. Give you the whole procedure. She will hold your hand through it, the whole thing, right? So these labs are really designed, are really at this point, it's so competitive in these labs that they will really hold your hand through the whole process. If you want to be on your own, you can go to NIOSH. You should check it anyway. You go to the NIOSH website. We can get online and we can even actually take a look at it. Here's a typical sample tube. Remember we talked about the idea of breakthrough, the idea that the activated charcoal filter might not catch all of the contaminant, which means that you won't realize some of it was there. Right? It's getting sucked through, so it's going through the pump in this direction. There's two sections here. See this over here? There's a little bit of fiberglass in there, and then there's 100 milligrams of activated charcoal, and then there's 50, and the air's going through this direction. The idea here is that you're pulling air through this at a certain rate, right? So you want to make sure that, or the lab will make sure that when you send it to them, they analyze this, pick a contaminant that you might, anything, right? Any organic.
Formaldehyde.
Formaldehyde. You wouldn't use this for formaldehyde, that's the wrong one, but that's okay. Let's say formaldehyde, right? So let's say you're measuring formaldehyde, right? You pull whatever the NIOSH procedure says, you pull, let's say it says 50 liters of air at 1 liter per minute. You pull that through, you set up a pump, run it for 1 liter per minute for 50 minutes if you're doing area monitoring. Remember, with workers, a little bit different, right? And you pull the air through here, and then the formaldehyde doesn't, but we're going to assume it gets absorbed in this 100 milligram section, right? Yes.
Xylene?
Oh, xylene. Yeah, xylene is good. This one's good for xylene. Okay, so xylene gets absorbed in here, right? Right. Xylene gets absorbed in here, right? And you know how much air you've pulled through here, right? You send it to the lab. They tell you how many milligrams of xylene were caught in there. So now you know if you sampled 67 liters of air, it had 23 milligrams of xylene. Not that much, but let's just for the argument's sake. What did they do with the other end? They analyzed that for xylene too. If they find xylene in there, what does that mean? It got past this section. There was more than 27 milligrams in there. How much was in there? We don't know because it got into the second section. Could have been anything. Could have got through the second section, right? So we want to make sure there's no xylene in there. That's why that second section is there. It's there to measure if there's breakthrough. If there's breakthrough, you didn't capture all of this stuff in here, the lab will tell you, oh, you got to do this again. No good. And one of the reasons that might occur is because you pulled air through there too fast and the sorbent didn't have time to absorb it, or there was more of a contaminant in the air than this could absorb. The level was higher than you anticipated. So it couldn't absorb all of it and it got through. So you got to do it again. If that's the case, you run it for a shorter time. Because a shorter time, you'll have less contaminant and you'll be able to actually get a real measurement of stuff.
Excuse me.
Yes.
So how would you know if, say, you're reading, when you're comparing the readings, which one is the most accurate? So for, like, if you're
oh, you won't know until you do it.
Okay.
Okay. One of the things you're doing is that you're making a judgment as to what you think is in the environment, right? If you're making a judgment, I think there's 10 ppm in the environment, so I'm going to run this for 100 liters, and it turns out to be 100 ppm. That's a problem. There's a good chance you're going to get breakthrough. You're going to have to go back and do it again, right? Okay. On the other hand, it could be less in there, which, well, if there's less than you anticipate, not so bad because it'll just say not detected. It won't be enough for them to detect. Yeah.
If you consistently keep getting breakthrough, that means there's a lot.
Yeah. Yeah, you shouldn't consistently keep doing it. If you do it the first time you get breakthrough, you should probably go back. And you want to know something? We're about to see something that's gonna make things a little bit less make it a little less likely to occur. But yeah, what were you saying?
No, I'm saying if you keep getting breakthrough, that means there's a lot in the atmosphere.
Right. Or you're pulling it through too fast.
But you could, I mean, like there's a mass spill, let's say, and you're not noticing it, so you should probably take that out.
Yeah, sure. And we're about to see something else. See this device over here? This is interesting. This actually holds, this connects to your pump. And this actually holds 2 tubes at the same time. And it's got a little screw in the bottom, little screws in the bottom here, which are little flow adjusters. And you can actually set this up so there's 1/10 of a liter per minute going through this tube and 1 liter a minute or 1/2 a liter per minute going through the other tube. So it stretches out the range. So it makes less likely that you'll be pulling not enough air or too much air. It spreads out how effectively that you'll get this range.
Fails, you more likely know it's due to.
Yeah. Or in fact, it may not fail. One tube may be saturated and you'll get breakthrough, and the other tube will be okay, with the lower volume will be okay. You won't get breakthrough, so you get a
But you couldn't tell how much is in the tube without sending it to the lab, like visually. It would be changing the tube.
No. There are colorimetric tubes, which I just told you about. Some of them use a hand pump. Some of them actually use a regular pump, right? An automatic pump to do the same thing that you would do with your hand. But they actually do change color. We'll dig them out. Over the course of the semester, you're going to play with all this stuff. That's the best thing about this is that it involves a lot of toys. Here's a pump, typical pump. It's got, this particular pump has something called a rotometer built into it. It's a little ball. You really can't see it here. There's a little ball in a glass tube that's marked, has markings on it. That the ball goes up depending on how much air is going through the pump. So you can use that rotometer, that ball, you can adjust the flow rate so you know whether there's a tenth of a liter of air or 2 liters of air or half a liter of air being pulled through that pump. It's a problem with that. That rotometer gets a little dirty over time. It's not reading quite the same. It may not be manufactured perfectly, so on and so forth. So that rotometer may not be perfectly accurate, right? So in order to make sure that we're pulling the right volume of air, which is critical to our measurement, in order to make sure we're pulling the right volume of air through the filter or the absorbent material, right? We have to know what that volume that's going through that pump is. We actually have to calibrate that pump. That's what we're going to be doing next week before we actually do the sampling. And tonight we're going to play around with that tonight. We'll just set it up and play around with that a little bit. This is a passive air sampler. 3M makes a bunch of these, right? They make them for formaldehyde. They make them for a whole bunch of other stuff. They even make a version of it that you can hang on your collar, and you can tell them that you can pick out of a list of about 100 VOCs. You can pick 3, and they'll analyze those 3 for you. Anybody got any idea what kind of instrument they use to identify and measure the amount of VOCs in these kind of devices? Okay, what do you think for VOC? Gas chromatography and sometimes mass spectroscopy. Okay, so what is that stuff? We got one over there. One of the students actually got it working a couple of semesters ago. We actually have a student version of a GC. We'll actually, when we get to that point, we'll actually open that thing up. I don't know if we'll get it working, but we'll open it up and you'll see the parts of it. GC is like really pretty simple device, considering considering how sensitive and accurate it can be if it's properly calibrated. It's actually pretty simple concept on how it works. Okay, sorbent material, you send it to the lab. They put it in that machine one way or another. We'll talk about that. And they measure how much of that is in that passive device. The difference here is that in the sorbent tube, you're removing all of the contaminant as you pull the air through it, so you know what was really in the air. This one depends on the amount that's going to be absorbed on air is going to be changing all day long. It's going to be, when it's really concentrated in the air, it'll get absorbed. But then when a low concentration in the air drops, some of it may come out of that passive device back into the air. So it kind of reaches kind of an equilibrium. So it's a whole different ball game. So this is not as reliable as using those sorbent tubes. So this is a good survey device, something you do to figure out whether or not you might have an issue, right? Is this satisfied? Will this satisfy OSHA, PEL for OSHA? No, not even if you keep it on for 8 hours, right? Because you got to use the NIOSH procedure, which involves the pump for OSHA. Okay, particulate sampling. Relative sizes. One of the issues with dust and particles in the air is that depending on the size of the particle, it can have different effects on your respiratory system, or it might be absorbed differently in your body or affect your respiratory system. Particles less than 100 microns are inhalable. That means they get past the nose hairs and whatever gunk you got on the back of your throat or whatever when they hit. Now keep in mind, there's a couple of ways that your body keeps junk out of your lungs, right? One of the ways is just by making turns, right? So what does your respiratory tract look like? Well, starting, you got your nose, you got sinuses, all these cavities, and you got the back of your throat, and it goes down your throat, and you got your trachea, and you got bronchi, and then you got bronchioles and stuff like that. What's happening when this happens? What's happening is you're breathing air in, it's got to make some turns, gets caught up here, and so large particles tend to not like to make turns. They have mass, they don't make turns so easily, right? So they wind up impacting mucous membranes and getting stuck. So the bigger the particle is, the further up in your respiratory system it gets stuck, right? So when you get down to your bronchi, the same amount of air has to go through smaller tubes, right? So now the air's is increasing in velocity. So it makes it even harder for these particles to make turns and not get stuck on mucous membranes, right? So as it goes down into your lungs, as the particle gets smaller and smaller, it makes it easier for it to penetrate into your lungs. And as it's bigger and bigger, it's stopped further up your respiratory tract. So inhalable is 100 microns. Thoracic, which means basically, I guess, your upper respiratory system, is 10 microns. Once you get down into 4 microns, that's considered respirable dust, right? That means that the particles are so small that they get way down into your lungs and get into areas where there's unprotected living tissue, right? Alveoli and stuff like that, where there's unprotected living tissue, but it can do some real damage or get absorbed and stuff like that.
How does that work for cigarettes? Is it like
Oh, they're tiny. I don't know. We'll see. I think there might be another slide. At some point when we get it, if we don't look at it this week, we'll look at it next week, but they're tiny particles. So obviously they go way down into your lungs. That's half the point, right? Smoking gets into your lungs. Well, I'm not sure why, because you taste it up here. I guess, excuse me. I know why people inhale smoke, because cigarettes are not really about the taste. They're nicotine delivery devices is really what they are, right? And for that to work, marijuana, for that to work, you have to inhale it into your lungs, into the alveoli, so you can absorb the nicotine or the other materials. So I'm sorry, you were saying. Okay. So at any rate, 4 microns and lower are called respirable. They're really most concerned now about really ultrafine particles, which usually they define as smaller than 2 or 2.5 microns. And the reason why they're concerned about those is those really get down into your lungs because they almost behave like a gas. They're so tiny and light and have so little momentum that they almost go through your entire system, almost as if it's a gas. So they really can get down into your lungs, and they're really the most dangerous. So you may see some reference. Remember we just talked about particulate monitoring, right? The size of the particle is important. One of the standard we're going to be dealing for nuisance dust, right? They're going to ask us to measure total respirable particulates, total particulates and respirable particulates. So we're going to use a device that allows us to measure all of it, right? In other words, just catch everything on the filter. And another device we're going to add to it that'll remove all the particles that are bigger than 10 micron before it gets to the filter. So all we're measuring is respirable particulates, okay? Or what we're calling, depending on the device, it might be 4 or 10 microns. And there's a nice picture with a lot of nice stuff there. Ultrafine, 0.1 micron. Okay, there's a variety of pumps there. A lot of nice pump pictures and stuff, and they're all different sizes. What's that? You got yours? Yours are up there?
Top right.
Oh, there you go. And the one on the top right one is for high volumes. We're going to be using a pump like that for collecting mold spore samples. We're going to be a pump like that you would use a pump like that for collecting asbestos sampling. We've got to move a lot of air fast in order to do those collections. The other pumps are small because we're measuring things that we can deal with smaller volumes, smaller flow rates, and also they're small because they have to be portable so a worker can wear them for 8 hours, right? Asbestos, we're doing area monitoring. And that's one of the few PELs, I guess, where you actually do area monitoring instead of personal monitoring. Okay, and now here's a typical setup for measuring asbestos. See that black cartridge there? That is specific. It's 25 microns in diameter, right? And it's about yay long. And they use that for, usually I get to this class about an hour ahead of time. So I got all this crap laying on the desk. We can pass it around. I'll try and do that for the next time. But they're yay long, and you hook them up on a sampling train like this with a stand so that they're up off the floor, like in a breathing zone, because you don't want to. You want to catch a breathing zone sample. You don't want them on the floor so that when people walk around and kick stuff up and stuff, you're measuring what you would be breathing if you're lying on the floor and not in breathing zone. So you set them up on this stand. They're usually tilted a little bit downwards so you don't catch a lot of extraneous particulate in it that somebody might drop into it or something like that. These other cassettes are 36 37, I'm having a senior moment, 37 millimeter or 35? 37. They're wider. 30, I think it's 37 millimeter, right? And they have filters in them. Both of them. This one has a filter in it too, right? The asbestos cartridge has a filter in it, but it's long and narrow, right? The other one has a filter in it, but it's short and stout, right? It has a little, you can have it open faced, or sometimes you leave it on. There's a little hole in the middle, and you suck air into the little hole that's still over there. Okay, and what you do is you can either buy them from the lab pre-weighed. See that this one has a weight on it, an ID number and a weight. You can actually buy it from the lab pre-weighed, suck air through it, know the volume of air, send it to the lab. They pull the filter out, reweigh it, and tell you how much was how much the weight increased, and we'll do a calculation on that. We're actually going to do that. We're going to weigh them before and after, and we're going to expose our own. Okay, so that's cassette. Anybody have any idea why asbestos we use a long, narrow one, and with other particulates we use a short, stout one? What do you think? If I'm measuring dust in the air, what's my report? What units is my report going to be in? Right? I'm going to measure the difference in weight. It's going to be milligrams per cubic meter, right? Okay. If I'm measuring asbestos, what's my report going to be? Fibers per cc of air, right? So in this case, we're measuring a difference in weight. In this case, we're measuring the actual number of fibers. So someone is going to have to take that filter, put it under a microscope. Okay, it's going to be you. Okay, put it in a microscope and count the number of fibers that are on there. How long, if I have a 25 millimeter filter and it's run in a typical environment, let's say it's in a workplace where they're doing an abatement and you're expecting about 2 fibers per cc or something like that. Right? It's a little bit above the standard, but you expect maybe it's inside the work area. 2 fibers per cc. How long do you think it'll take you to count all of the fibers on that filter? If they ran that pump for a few hours. How long do you think? Hour, 2 hours? You'll be dead before you count all the filters on that filter, right? The way they count the filters, they put it under a microscope, and that microscope has a little scale on, a little circle with a scale in it, and you're looking at a tiny, teeny, tiny portion of that filter, right? And the way that you look at it and you take a reading of that tiny amount, and then you generalize that to the whole filter. There's a problem with that. You might get an area that has a lot of fibers, might get an area that has a little. So you take you take 20 of those readings, let's say an average, right? How much of that filter have you covered now that you've taken 20 readings? Practically none of it, right? You're just getting 20 readings, but you're still not really counting the whole thing. So it's important that the fibers be evenly distributed over that entire filter. That's why you use a long cartridge. It gives the air a chance to get into it's something called non-turbulent flow, so that like the fibers, when they're caught in the filter, are evenly distributed. Where with that other one, if you're coming in through that little hole, they all wind up mostly piled up towards the middle or something like that. But you don't care because you're measuring the weight. You don't care how to distribute it. That's why they use that kind of filter, long and narrow, and the other one is a short stout filter. See, now, is that useful to you? Probably not. But you probably could have lived with just knowing that used the black long one. It's nice knowing that stuff, right? Now, there's 2 kinds of filters. You have filters that actually have pores in them, like these PVC filters. They actually have holes in them that are a size that they catch a certain percentage of the fibers of the particles within a certain size. And then you have like other kinds of filters, which are what they call tortuous pass filters, where they're kind of layers of material, almost like woven, where the particle has to like make turns, as we were talking about before. So the bigger particles get caught, and usually they're rated for a certain efficiency, like get 99.9% of the particles that are 4 microns or bigger. But your choice of the filters is determined by the standard that you use, the standard that you're applying, the NIOSH rules on how to take that filter. One of the reasons you might use a PVC filter, because you might be in an environment where there might be moisture that might affect the other filter. Okay, they're moisture resistant. they're not hygroscopic of moisture. That's kind of like what that 5 micron PVC filter looks like. That's the size of the holes in it. Hydrophobic, doesn't absorb moisture. They get staticky though. We actually have a little beta emitter, a little radioactive plate in one of these scales here, where you take the filter and you kind of drag it across it, and it kills the static charge on the filter media. Okay, it's probably past its half-life about 9,000 times already. It doesn't work anymore. We still make believe that it works. Okay, so high volume samplers. These are samplers usually used for ambient air quality, outdoor air. You guys seen these around the city? Usually, they used to put them out like this, except I think people were stealing them. So now they're inside cages, right? And they leave them there for a day, and they come back and pick them up. And every once in a while, you see, walk on Madison Avenue, you see this cage with this kind of like little dome coming out of it. And they're actually sampling the ambient air. You may also see there. You actually can go online and actually see where the water sampling devices are. Cities required to take a certain number of water samples based on the number of locations that it supplies water to. 800,000 service points in New York City. So they might be required to do 250, 300 samples a day, right? And they collect these samples not just from the reservoirs, they collect them from these collection points all over the city. They kind of look like, I don't have a picture of one. They're steel boxes, right? About 2 foot by 2 foot by about 2.5 feet tall, and they're on pedestals. So they literally have a lock on them. They open them up. They draw a sample. They take them back to the lab. But you'll see them. You actually can go online. Those are permanently piped in, so you can actually go online. What contaminant do they not measure that they have to find another way to measure in water? Think Flint, Michigan. Lead. Problem with lead is is New York City giving us water with lead in it? No, they're not. Right? The lead's not in the reservoirs. The lead's in the building piping. Like the street mains are made out of steel. Some older houses, I have a house like this. Some older houses have lead mains from the street to the house itself. The homeowner's responsible for that main, by the way. If they want to replace it, they got to pay for it. Right? So they got lead mains. Usually the mains themselves usually not a problem these days because they're so covered with, they're 80 years old, they're 100 years old, so covered with crap that you're not really leaching much lead off of them. What's a bigger problem in many cases is not the lead main leading into the house, but the older piping in the home. Because for a long time, people would install yellow brass piping or brass piping. Brass piping could have as much as 9% lead in it. They add the lead to it to make it machinable. So they can make threads on it easily and stuff like that. Forge fixtures out of it and stuff. So there's lead in the brass piping. There's even more lead in the copper piping, but not in the copper piping in the solder that they used to join the copper piping up until about 20 or 30 years ago. Right? And what happens to that lead? Well, water from the city in New York City happens to be a soft, low mineral surface water. It's in lakes and stuff. Doesn't percolate through the ground and pick up a lot of minerals. Very soft, low minerals, like rainwater almost. And those kind of waters tend to be very aggressive to piping. So it sits in your piping in your house. It corrodes the piping. You get some lead into there. And lead, we're talking about really, really tiny amounts of lead that can have a health effect, especially with children or pregnant women. Right? Builds up in the water over the weekend. Whatever, when you go away from the weekend, you come home, I say, let's make some tea, and you make yourself a nice hot cup of lead when you take that first drip out of the faucet, right? Now, what's a good way to prevent being exposed to lead? Run the water, right? You run the water until it gets, my old man, he was a construction worker. And when he used to, he worked hard out in the sun and stuff like that, you can imagine, right? So when he used to come home, he liked nothing better than a nice cold glass of water. And he used to, when I was a kid, so my job was to get him his cold glass of water. That was one job. It was what they call a timberman. I don't know, you know when they put an excavation in the street, right? They have to build up, they have to use timbers to shore up the excavation so it doesn't collapse on the workers. I had no idea how important this was back, that I don't have to tell you guys, are industrial hygienists now. You know that collapsing of excavations is like a major hazard for construction workers, right? So that was his job. He was a foreman on a construction crew. He was a timberman, right? And AFL-CIO, local 36, right? I remember, and they used to handle these timbers. They used to put up these, and they would reuse all the old timbers, right? So you can imagine these things got pretty nasty after a while. He used to come home with splinters you would not freaking believe, like logs in his hands. And it used to be my job to dig them out, right? So because by that time he was pretty old, he couldn't see that well to dig them out himself. So that and get him but I remember every time he came home, give me a glass of water and let it run, right? So he would make me let it run for like 5 minutes until it came out as cold as it possibly could get before he would drink it. But so I guess maybe he didn't have to be an industrial hygienist to know you need to let the water run, but make sure it's good, right? With filters, it is possible to use filters to remove lead. There are filters. There's an organization called National Sanitary Foundation that certifies filters. And what you want is a filter that's certified to take out lead. Now, that's not a filter that's a media filter. In other words, something that just takes out dirt. That's not a filter that takes out chlorine like activated charcoal. That's got other media in it that will react with certain metals and take them out. So it's got to be specifically made for lead. The other thing is you can't put it on the house. You got to put it on the point of use. Because if you put it on the house, the problem is the piping inside the house. So you need to use it right where you're going to get the water. It's got to be the last thing that the water goes through, right? If you're going to use a filter to remove lead. But yes, you can have point of use filters for lead, right? I know somebody that makes a point of use filter for a shower for lead. Why you need one for lead, unless you're opening your mouth and drinking the water, I don't know. But a lot of people are so concerned about this stuff that they have a demand for that. What happened in Flint? Why? How did things go wrong in Flint? Anybody know?
Wasn't it about the pipings and like the corrosion?
Yeah, but why? The piping's been there for 80 years, 100 years. Why is it now? That's right. They used to buy their water from an adjoining community. It's to pay for it, right? And they ran into financial difficulties about 10 years ago. They went into receivership. They went bankrupt, basically, the town. They went into receivership. And under receivership, they had to start making big cuts. And one of the ways they decided they could save money was to take water out of the river. I don't know what the river, is Flint River? Is that what it's called? Take water out of the river and use it for drinking water. Okay, now that's not so bad. You filter it, you treat it. You can use almost anything for drinking water. You treat it properly. Yeah, well, yeah, it has its issues. Let's put it that way, right? But it didn't have lead in it. Lead was not the problem. The problem was they didn't have a big lead issue there because the community they were buying the water from was using groundwaters, deep wells, which had a lot of minerals in them. Waters with a lot of minerals tend to be depositing material. They tend to drop out mineral on the inside of the piping. So the big problem with water with a lot of minerals, hard water, is that you're going to scale up your piping, and you'll scale up your hot water heater, and you actually can look at it. You can see like rock forming on the inside of the pipe or whatever. Yes.
Well,
yeah.
It's like it kind of looks like protective coating.
Yeah.
For the pipe.
Exactly right. So you don't have lead problem. Then you switch over to the other supply, and that supply now, the river water is surface water, very little minerals in it. And it's very aggressive. Doesn't tend to drop out, but it's very aggressive. So now you're putting water in through that old piping, which now is capable of leaching the metal out of it.
It's like soft water?
So exactly right. Soft water is the terms soft and hard refer to the fact that there's certain minerals in the water, calcium and magnesium especially, that tend to affect the way that water produces soap suds. So with hard water, there's a lot of calcium and magnesium. Right? But there's also a lot of other minerals, but the ones that everybody's concerned about, calcium, magnesium, because it reacts with stearates, soaps, and produces like these scums and these other materials, so you can't get suds out of them. They don't feel right when you wash with them and stuff like that. They scale up the pipe, right? So that's calcium and magnesium, but there's other minerals in the water also. Soft waters have very little calcium and magnesium, so they call that soft, hard and soft. But they also their overall mineral content, not just calcium, magnesium.
Good thing they asked an industrial hygienist these questions.
Yeah. Well, that's a good question. Is that what got them into trouble? Doing that? Not necessarily.
I think they knew about it, but they didn't.
Exactly. It's the same old thing, right? It's the goddamn emails. It's the goddamn this. It's the whatever. They knew about it. They didn't do anything about it.
They
Right.
actually spent more money trying to fix the problem than what they actually thought they would save by
Right.
spraying water.
Exactly. Well, as it happens, New York City has an issue with lead because we have soft water. We have an older housing stock. New York City has been battling with the EPA for the last 40 years over excursions in the level of lead that exceeded the EPA's maximum contaminant level. It's a statistical standard. It's not every sample. Less than 10% of the samples are allowed to be over 15 parts per billion, I think. As long as less than 10% of the samples are over a certain amount of lead, the EPA says you're okay. And now health people, their attitude is no lead's okay, right? That's from a health perspective, no lead's okay. On a practical basis, they're not going to repipe the whole city of New York in the next 3 days, right? So on a practical basis, the EPA has a limit. That's a statistical limit. You get 11% of your samples that are above a certain amount of lead or lead and copper. There's a lead and copper rule. It's complicated. Once you get over that over certain statistically over that, then you can get fines, you can get regulated, and so on and so forth. The city's been battling with the EPA over that particulate matter in the water, cloudiness in the water, rust in the water for ages. And the deal is the city finds ways to accommodate them whenever they really come down on them. Right now, the city is adding a phosphate-based chemical to the drinking water, treating your drinking water with a chemical that reduces the corrosion rate on solder and other kinds of materials that tend to have that kind of material. They tend to have lead in them, right? So they're adding a chemical to reduce the corrosion rate. I'm really talking a long time here, I know. Let's take a break, right? Otherwise, we'll all be asleep. We'll take a 5-minute break, take a quick one. We'll come back for about 20 minutes, and then we'll split. I want to just show you some stuff that's over. I want to go through the last few slides and show you the pumps and the trains. Okay, 5 minutes. Come back. Let me just show them this equipment. Yeah, I was just hoping for one pump or something. You brought the whole works here. Okay. Do we have any cartridges? Yeah, it's a mess. I think he might have been in a rush when he packed it. How about, do we have a one of those calibrators? Like the,
Yeah.
we might have one here. I'll take these photos. Another cartridge. I'm just going to show them the equipment, and then I'm not going to run it. But next week we're actually going. I want to get at least 5 setups, so we can have like 2 or 3. So we can work in teams of 2 or 3. Okay.
Do you think that the home kits for lead that they sell at the pharmacy, do you think they're good?
They're okay. They're not great. They're not perfect. You mean the ones with the pen where you rub it?
Yeah, I want to test the lead in my building. The drinking water.
On the drinking water? Yeah.
Because they have old pipes, so
let's talk about this when we get to that part of the semester. Maybe we can find an excuse to get onto the paper a few sample analyses. Okay, let's see what we got here. There's a locometer, that should be interesting. Some sorbent tubes. Sorbent tube and maybe a cartridge. Yeah, we're gonna have to get
My boss was so tired. Yeah, great. Thanks.
Okay.
Thanks for noticing.
What happened to the oven? The oven somewhere? The little ceramic oven? Oh. Yeah, they warned me about this.
Usually 10 minutes.
Where you going?
Usually,
What time's your class?
25 minutes and then
You wanna get out of here by 7:45?
Yeah.
10 minutes, yeah. Okay. Yeah, 20 minutes you'll be able to walk over there. My problem was I drove back from there and I had trouble parking. I got behind a truck. Another guy got in my way. Huh? Parking on the street is no problem here. Parking at 125th Street is a problem. But that parking, well, no, it's not a problem. It's just expensive. There's a lot in the building. No, out here, metered parking. This is easy. This is metered parking or whatever.
There's nobody that lives here wants to park on the meter parking.
Why not? Oh, yeah. Well, yeah.
It's fine for you. You're on there for 2 hours.
Yeah. Okay, guys.
People are like, oh, I gotta leave at 9:30.
Okay. Okay, guys. I just want to show you that there's other sampling devices. This is called an Anderson sampler. You actually put Petri dishes inside this thing. Here's this is one section of it. You put a Petri dish inside there. You suck air through it. The air impacts particles onto the surface of the growth media, and then you incubate it and you actually count like mold spore counts and stuff like that with it. So yeah, that's what it looks like when you're done. We're going to do that, by the way. You're actually going to take one home with you and expose mold spore plates at your house. Or it doesn't have to be at your house. You can do it anywhere you want. Yeah. Okay. So now this is what we're going to be doing next week. Here's a pump, right? This is the pump we were talking about. Oh, I'm sorry. This is a calibrator. This is a dry calibrator. It's got a little piston in it, right? Okay. Normally, what we would be doing is we would be taking a sampling pump. We would be connecting this sampling pump to a sample train. Don't let that roll off of there. Okay, we're connecting the pump here. We would put our sampling device on the end of this. This actually gets installed in here. I'm not going to bother trying to figure out which is the front end, which is the back end. Actually, I can at least do it in the right direction. Okay, so this gets installed in here, a holder. It's just a holder. You really don't even need to use this if you don't want to. And this would go into the top of this thing. Right, so now that when we turn this pump on, it's going to pull air through this cartridge at a given rate, right? And a worker could wear this on his belt and hang this from his collar. And at the end of the day, we'd be able to tell how much of the particulate we're interested in went through this. Might be just dust, might be wood dust, might be silica, might be so on and so forth. Might be a lot of different materials, particulate-wise. Okay, if we're looking for organic vapors, instead of connecting this to this kind of cartridge, we would use a sorbent tube and hang it here. Okay, if we're asbestos, we would have a pump, a big pump, and we would have it on a stand, and it'd be pulling air through those activated charcoal filters. So what's on this filter? What's on this filter? If you look in the back there, you can actually see it. There's a hole on the end here. If I open this up, there's actually trapped in the back of this, there's two layers. One layer is a backing layer. Air particles pass through this very easily. The other layer is a filter. Very fine little filter. Before we start, we weigh this filter. We install it back in here. We pull air through it. And when we're all done, we take the filter back out again and we reweigh it. That tells us how much air, how much dirt, how much particulate that this filter caught. So we're going to be doing that. We also maybe will do a couple of activated charcoal filters as well if we get a chance to do it. Well, this part of it, this particular one was actually supplied by a lab. And it used to have a number on it. And you could send it to the lab and they would weigh it before and after. You don't even bother to open it. You just take the little caps. There's a blue cap and a red cap. They actually indicate front and back, right? And you would send it to the lab. They would reweigh it and give you the result. You'd be all done. We're going to do it ourselves. We're actually going to weigh it, put it in here, and so on and so forth. If you're going to send this to one place you could have some error is in the weighing process, right? Certain amount of precision from the scale. Things could go a little bit wrong there. That's one place you could go wrong. But the bigger place you could go wrong is this pump works on a battery, and we're going to suck air through this device, and we have to know exactly how much air we're pulling through here. So there's two ways to do that. One way is to actually read the pump. Battery's dead. One way is to actually read the pump, and the pump will display the rate that the air is flowing through here, but we can't be sure that that's correct. We need to calibrate it. We need a mechanism that will tell us exactly how much air is going through this. Okay? That's what this is going to help us with. This is the primitive way of doing this, right? The modern way of doing it is to use this device. This is a piston type calibrator. There's a tiny little Teflon coated piston in a tube in here. And we hook up our pump over here. When we turn it on, if we press this button, it releases that piston, and the air that we're sucking through pulls up that piston. It's virtually frictionless. So that piston passes two optical sensors. And the speed at which it passes those two optical sensors tells us the flow rate. It comes out. You read it out here digitally, right? This is a standard. This is really a secondary standard because it has to go back to the manufacturer every year to be checked, right? So what we can do instead of doing this is we can, if we don't have this available, we're cheap, we're in the field, or we love industrial hygiene, we can use this instead. And this is a burette, right? Volumetric device, right? We know that this has been designed, so this is 0, that's 1,000. This is exactly a liter of air between here and here. That's the way this is designed. Basically a primary standard, right? So we can set this up in a stand, right? Like so. We can connect our pump to the top of this thing, and we can start our pump running. Take a beaker with some soap solution. We hold it up here. A bubble will start going up this column. That bubble is essentially a frictionless piston, just like this. So we can time how much time it takes it to pull 1 liter of air through here, right? Now, normally, if you look in the drawings, this is using the pistonless for dry cal flow calibrated frictionless piston, right? I might have a picture of the burette. See, with the burette, you see them using a little chamber here in between the pump and the and the burette. The reason for that is you don't want the pump sucking up soap, right? But we're going to be really careful, right? We're going to use a nice long tube. We're not going to let the pump suck up any liquid because we don't have a chamber to use that way, right? So, but what's going to happen is we're actually going to take 3 measurements with the pump, and we'll take the average measurement. That will be our calibrated pump volume. Okay? We're going to then use it to measure. We're going to run it for half hour in an environmental chamber that has dust in it, and we're going to take the filter off, and we're going to then calibrate this pump again. Why am I calibrating it before and after? Anything that works on a battery is not going to work as efficiently after it's been running for a while than before. Presumably, this has some sort of functionality that should even it out a bit, but you really can't depend on that. So we're going to calibrate it before, calibrate it after, and then assume that the actual flow rate that we had was an average of the before and after. I'm going to give out some sheets of paper. I'm going to reprint them for you next week, just so you have them now. You can take a look at them. And we're actually going to take measurements like this. Okay, here we go. And we're going to actually measure the flow rates and we're going to measure the weight change and so on and so forth, assuming I can get any of this equipment to work. We've got at least some of it working, I think. Okay. Here's kind of a data sheet. Like I said, I'll reprint. If you remember to bring them, great. If not, I'll reprint them. Okay, and I'll actually post a spreadsheet online where you can actually do the calculations online. There you go. There you go. Pass those back. And there you go. You can pass those back. There's some extras over here. Did everybody get one?
Yep.
Okay, good. All right, so we're gonna do those actual calculations. We're gonna measure the flow rates, the weights. By the way, this thing over here is called a rotometer. That's a little device with a ball in it. We can actually calibrate that rotometer. In other words, we can connect a pump to it and a burette to it, and we can use the burette to tell us when 1 liter of air is going through that rotometer, what does it read? Let's say it reads 0.9. And when 2 liters of air is going through it, what does it read? Let's say it reads 1.82, right? You can then make a chart, draw a line between those readings, and use that chart so you can correct the rotometer for the actual volume. In other words, you can use a primary standard to calibrate a secondary standard so you can use that in the field if you can't bring the primary standard. Okay, these guys have to leave.